Okay, class, we're back now, and we're ready to talk about the loop of Henle. The loop of Henle. Now, let's see what we already know about the loop of Henle, what we've come up with now. We said that there were three positions for nephrons: the outer cortical, mid-cortical, and juxtamedullary. We said that the loops would differ in length, whereas the longest loop of Henle was located in the nephrons that were juxtamedullary, intercortical. We said that the job of the loop of Henle's main job, the long one in the juxtamedullary, which also had the vasa recta around it, was to be able to concentrate the urine. And we said that the concentration of urine is important to control your blood osmotic pressure, that we'll talk about in another time. All right, so the functions of the loop of Henle, this hairpin shaped thing, it is to further perform reabsorption. So remember, we only did some reabsorption. For example, we only did 80% of bicarb in the proximal convoluted tubule. If you lost 20% of your bicarb, you'd be dead. So tubules after the proximal convoluted tubule's job is to find, adjust, and bring back the amount of bicarb you need. And again, you wouldn't bring as much back if you had alkalosis. So it helps with acid-base relationship due to its sodium-hydrogen antiporters in the thick ascending limb. A major function is to control osmotic pressure. Okay. So the longer the loops, the more ability. Now, this sodium-hydrogen antiporter is big in holding on to sodium and getting rid of H+. That means you would invoke this a lot if you were acidic, because you would try to get rid of as much H+ as possible, which is acid, proton donor. All right, let's go a little further here. All right, so the design of the loop of Henle is basically this. We'll look at this real quick. The design of the loop of Henle is that you have a descending thick limb, a descending thin limb, an ascending thin limb, and an ascending thick limb. So in other words, you have descending thick, descending thin, ascending thick. Okay? The descending thin has like simple squamous, ascending simple squamous. These are cuboidals here, cuboidals. Okay? All right. So when we look at this, we'll go a little further there. You can see here those thin segment cells in the thin limbs of it. Okay, so we go here. All right. Now I want to go to this here. I'm going to say, find it here. Okay, this right here. I'm going to say the loop of Henle has different areas as we named. Okay, and what I'm going to do is take this slide here, copy it, and put it over here as I read that to you. I'm going to put this here so you can see the picture briefly. All right, now I'm going to go to this here. All right, so the loop of Henle has different areas, which we just named. The descending portions are very, very permeable to water. See, it's a lot of water you filtrate and it's coming out. The descending portions are very, very permeable to water. They have those aquaporins. Remember the water pores we mentioned, transmembrane integral proteins. They're permanent. They're permanent residents here. So therefore, water will come out. They're somewhat permeable to solute. So solute can come out, but not nearly as permeable as to water. So it's not impermeable to solute, but it's far less permeable to solute. So the main thing that comes out is water that exits. And remember, what comes out of here goes into the capillary surrounding. Okay. The ascending portion is not at all permeable to water. No permeability to water at all. Water has to stay in there. No aquaporins, never. But very permeable to solute. And even in some cases, actively transports it. You have here, which you can see in the text, and we'll see here, a 2-chloride sodium-potassium transporter. A 2-chloride sodium-potassium transporter I'm going to bring up in a moment. Okay? So we go further, though. Because of the differences in the permeabilities in the different segments, the following occurs. The intraluminal, that means inside the lumen here of the tube, filtrate moving down the descending limb gets very concentrated. See right here, these numbers are osmotic pressure numbers. These numbers are, and we're going to review osmotic pressure, but osmotic pressure, the increase in the number is due to the solute. Osmotic pressure, assume a solution. The more solute concentration, the higher the osmotic pressure. So because water is coming out, the osmotic pressure is increasing, i.e. the concentration of solute, because water is exiting. When you come to the upside of this, the intraluminal filtrate moving up the ascending side gets very dilute. Why? Water is being held back, but solute is coming out, not only by passive diffusion, but also by active transport. So this side, osmotic pressure goes up. This side, osmotic pressure inside goes down. And that's going to be an important feature a little bit later there. All right. So we go a little further here. Okay. Now, the loop of Henle, okay, we'll come here, right, to this one here. All right. Now this here's the upside. See that drawing right there? This is the upside. So I'm interested now in this active transport thing I've been telling you about. This active transport thing. The loop of Henle sets the stage for independent regulation of both the volume and osmolarity of body fluids. Reabsorption of substances can be selective in accordance with the body's need for that substance and the body's need to maintain proper blood osmolarity. This is your normal blood osmotic pressure, about a 276. Some will say a 270 to 300 with about a 280 on the median. Okay, we'll talk about that a little later. I have something we'll read through. Okay, in this side up here, what you have, this is the tube, you have a sodium potassium 2-chloride symporter. Now let me explain. Okay, ladies and gentlemen, we are back again to an active transport of sodium. An active transport of sodium. All right. This right here is that old sodium potassium pump, even though they're not showing the potassium aspect of it. But this again is the sodium potassium pump here, ATP dependent. This is on the basolateral side. So sodium is being pumped out. Remember what I said, sodium creates a strong pull force, very exergonic, because it's low inside and the inside is negative. So sodium here on the luminal side has a strong desire to come in. Very exergonic, very energy, has a lot of energy. And what it can do is, the design of this symporter right there, look at that, will allow 2 chlorides to come in and a potassium. See, that doesn't change the charge, because if I bring 2 positives, I bring 2 negatives. You see what I'm saying? So therefore, sodium can be reabsorbed here. See, we only did 65%. Go back. We only did 65% of sodium in the proximal convoluted tubule. So I can bring some more back, because you would die if you lost 45% of your sodium. So I'm bringing some back. I'm bringing chloride back when we only did about a 50% chloride back. And then here's some potassium. Now, potassium, therefore, will get here, and some will kind of circulate. because we don't know how much potassium we need to bring back. Remember, this is fine tuning. This is fine tuning there. Okay? So that's what we're looking at. Okay, now some sodium potassium in this just diffuses out by diffusion. Remember here that this did some, the active transport, but just regular diffusion does some. Remember when we looked at that, we said some was just by passive transport. Okay? But the bottom line is that you bring in a lot of electrolytes back up in this area. A lot of electrolytes. Where here, on this side, you brought a lot of water back. Here, you're bringing a lot of electrolytes back. Okay? So that's what you're looking at in that loop of Henle. Now, the loop of Henle is going to set the stage for something a little later. So you got to understand this part. Because what it's going to set the stage for is concentration and dilution of the urine. But right now, I'm just kind of getting you to see what's there in that deal. Okay, so let's go back. The sodium, potassium two are located on the ascending thick limb. Reclaim this from the tubular lumen. Because potassium leakage channels return much of the potassium back into the fluid, the main effect of the sodium symportus is reabsorption of sodium and chloride, because you kind of bring this back here, the potassium. Okay? Now, so we go a little further. See what we got. The descending thick limb of the loop of Henle totally permeable to water, aquaporin 1, mostly impermeable solutes, but not totally impermeable. Ascending, not at all permeable. So you can look at this here. So we go back, and here's this. On the basolateral side of the thick limb has the sodium-potassium pump we talked about. So all of this we've talked about. We also have, which is not shown, a sodium-potassium antiporter. This is used for acid base that we can discuss a little later. But other words are also here. And what you're doing is you're using sodium and kicking back and getting rid of hydrogens. Okay? An antiporter, the way an antiporter works is this. Sodium would go in one direction and H plus would go. See, this is a symporter because you go in the same direction. Okay? But an antiporter is opposite. Okay? And it depends on what you need. Some 50% of sodium goes between the cells. Okay, so we see that. Okay, so here's kind of the summation of this. In the loop of Henle, about 35% of chloride is reabsorbed, leaving approximately 5%. Because you had about 60% reabsorbed in the proximal convoluted tubule. So you see we got 5% left for the distal convoluted tubule. Let's look here in my analysis. 20 to 30% of sodium reabsorbed, leaving approximately 5 to 15% to be reabsorbed later. Okay, because 65% was reabsorbed in the PCT. So depending on your blood sodium level and blood osmotic pressure, we're going to show a hormone that controls that. So right now, what we're sitting with is 5 to 15% of sodium still in the tubular fluid as it leaves the loop of Henle. And here, 20 to 35% of potassium reabsorbed, leaving 15 to 20% to be reabsorbed later, because 55% was absorbed in the PCT. And so how much you bring back depends on your potassium levels. Again, that's going to be controlled by this hormone. 20 to 30% of calcium. All of these things here that you've done in that PCT. So this kind of gives a tally, a budget sheet as to what you have there. Okay. So now we're to the distal convoluted tubule, and we're going to close right here.